Okay. So before I begin this talk, some of you may know all of these, what I'm going to go over. Some of you may be familiar with RISC-V. Some of you may not be familiar with RISC-V, and it's totally okay. All right. We're going to go over some foundational sort of systems programming concepts. So, but feel free to ask questions. I'll kind of pause throughout to take some questions, but I think we all come from different backgrounds, and I believe that I want to make this as accessible to people as possible. So just feel free to ask any questions. So hello, my name is Erik, and I work as an engineer at RISC Zero. And today my talk is going to be what RISC-V has to do with RISC Zero ZKVM. We're starting at RISC Zero. I realized that the name of our company is kind of a pun. So maybe by the end of this talk, you'll kind of get that joke. Anyway, so today we're going to start with some programming languages 101, right? So why do we write programming languages? For example, let's take Rust for example. We have code like this. Hello world looks like this, and some observations that we can make about programming languages is that it's meant for humans to read and to understand. This code will likely, and when you run it, it'll print hello world, but it hides the information about what's really going on underneath, right? So especially with Rust, what we typically do is we compile the program using a compiler to generate assembly code. Assembly code kind of looks like this. It has a lot of information about the system, about the computer registers, right? And there is some layers here, but for our conversation, the machine has these registers, so this instruction will say move the contents from here to here, load this value to here, and whatnot. So you can see that assembly tends to be really low level, as well as it talks about the system-like informations. All right, so let's take a look here. So this is the output from dumping, doing an object dump of compiled code. So on the left here are addresses, okay? And then in the next column are the values that are in those addresses. So if you're kind of looking at the file, it's just a bunch of these things right here. And then there's information that says, okay, we're gonna start here, and then in this address, we have this information. Now, when you run this, this is the actual translation of what these things are, okay? And so when you're running this, this assembly code, typically what a processor does is to fetch the instructions. So there's typically a starting point, starting address, and then we fetch the instructions, fetch the data, and then decode the data, and then execute the data, or execute the instructions according to RISC-V. And then we just kind of keep on doing this. And then when we execute, we typically increment the program counter by 1 unit to then go to the next instruction. But it's not always just we're going to execute the next instruction. Sometimes things like this instruction will say actually the semantics of running this instruction is to set the program counter to a different point. So you can kind of start going to different parts of the code. So that's how assembly is generally executed. Now the downsides to programming this is that we have very limited expressivity. Unless you actually read what this function does, you wouldn't be able to tell that this is a function that prints 1 character to the terminal. Right? So, and it's also very specific to architecture. So you can't just take this code and then run it on some other machine and guarantee it to work. right? And it's also, I guess this is the third point is like a little bit subjective, but it's also gets a little bit difficult to maintain. Although there have been some like pretty significant works that are written completely in assembly, like Roller Coaster Tycoon, for example. All right, so so it's kind of like back up here and look at the bigger picture. We have Rust code that is compiled using a compiler like RISC-C into assembly. And note, you may hear this ELF binary terminology. ELF is just like another, it's a name of a format of assembly code. So anyway, so now let's add a few more details here. Typically, so kind of zooming in, Rust or many compilers systems will compile to an intermediate representation called LLVM. Now, LLVM is really nice, which is an open source compiler intermediate representation. LLVM is really nice because it has support for many targets, many kinds of machines. So for instance, it has support for x86, so like AMD chips. So like this laptop right here is running x86, RISC-V, as well as ARM. So like ARM would be like Mac and stuff like that. And what's really nice about this architecture is that you can write front ends of compilers like so. So you have C, C++ compiling to LLVM as well, and some implementations like TinyGo will also compile to LLVM. This allows compiler developers to just only write a front end, and then the back end will take care of itself. So it helps developers by not having to write all of these back ends. Okay. Today, so let's kind of zoom in on RISC-V. So what is RISC-V? Well, there's two parts. There's this RISC part. RISC stands for Reduced Instruction Set Computer, meaning that each of these instructions will do like few and like simple operations. Okay, and in Y5, it's because RISC-V was like designed at UC Berkeley, and it was like their 5th RISC architecture instruction set. And also, what is RISC-V? To me, it's really just a specification. It's like this PDF. The contents that are in this PDF is what really outlines what RISC-V does, and what it does. And so let's take a look at this specification here. And this is kind of like in the context of RISC Zero as of now. So we have registers, and each register will contain 32 bits, so 32 ones and zeros. 32 bits, and as well as this special register called the program counter that will hold the address for the next instruction. Okay, and then on top of that, here is the RV32I base integer instructions. So you can see like we have addition, subtraction, and loading loading memory and storing memory, as well as branching instructions, and also like control flow. So this is like largely like most of it. Yes, Mash?
Sorry to pause you, because
yeah.
I'm getting a little lost, if I may re-ask, like,
Mm-hmm.
what do the instructions, what do they help with? Like you said that they help with making there be less steps, like for the compiler?
The instructions are like operating on these registers, okay, and to do the computations. They are like what like computations are doing. And does that kind of answer your question, or?
Yeah, so the instructions are basically like different types of like functions,
yes,
that are doing the computation.
Yes,
Gotcha.
yeah. And so like in addition to these, like we add this like feature. RISC-V is nice because there's a bunch of features that you can kind of like toggle, turn it on and off. And there's this multiplication extension. So that's just multiplication and division and remainders and stuff like that. So this seems pretty bare bones, but what's I'd like to point out the special instruction called the eCall, or the environment call. And these are special functionalities of the chip or whatnot. And so what you can do is load values to registers and then call this eCall instruction, run this eCall instruction, and the processor will know what to do. And this is like kind of different per each like processor. So for example, this will say like move the contents of register 10 to 11, move the value 2 into register 5, 2 into register 17, 1 into register 10, 1 into register 12. So we're kind of like setting up, like turning on these like knobs and then saying go, essentially. So this is like how a lot of like computations like, happen. So anyway, so that's kind of like how these things work. But what does it also look like? Well, there's like a bunch of implementations, and one of them is like this board. This board I think is 32-bit, or maybe it's 64-bit RISC-V processor. But you can also implement it as a virtual machine, which is kind of like it's an emulator essentially, like one of those Game Boy emulators, except it's a different instruction set. So the virtual machine, in code, we will implement like these registers as well as these the machine's memory, as well as how the instructions are executed. So all of this is being done in software. And I wanted to go over that point because sometimes people hear RISC-V and think, oh, we're like a hardware company, but it's really just like we're talking about the virtual machine here, right? So let's go back to the bigger picture here. So we start with some Rust. We compile to a RISC-V binary, and then we can use the RISC-V virtual machine to run the program, and will result in some answer or a state change, or like maybe you print like hello world to the screen or whatnot. So that was kind of like a quick intro into sort of like the systems background. Does anyone have any questions before we go on? Armando?
Yes.
Microphone? There you go.
Yes. You said that you can use Rust, C++, and Go as well, but is there like a deficiency if you use other languages, or is the same kind of efficiency with any of them?
A great question. So sometimes these languages, we have different languages because they allow the programmer to control, like have finer grained control. So for example, the C language will let you do a lot of manipulations, and the compiler, the language rules will allow you to do very minute things, but also kind of like make some common mistakes. But on the other side of this sort of like spectrum, like languages like Go, you relinquish more responsibility to the language so that it will do things for you. Now, there is like sort of a price to pay for a language like Go, because what will happen is that it will allow you to allocate memory. And one of the costly things is like it'll allow you to allocate memory, but then Go will clean it up for you. And the process of cleaning up this memory is called garbage collection. And that tends to be pretty expensive because what you're doing is going through these memory regions and traversing them to say, are you like a live heap item? And if not, if you're not being used, then I will remove it. But after it's being removed, then we typically these algorithms will try to like compact the memory so that the heap area doesn't look like Swiss cheese. It'll just kind of try to squish that. So all of that adds cost, but and I think it's kind of like a trade-off, right? Depending on your use case, like maybe like maybe you're writing some application that is not as performance intensive, and maybe you could afford the costs. But on the other hand, like it might not. And so like with Rust, where Rust lies is like it will allow you to do a lot of finer grained control, but there are a lot of nice language features that prevent you from making common mistakes. So yeah, that's kind of like an overview of your, yeah.
So the most efficient will be Rust, and if you need C instructions, you can also do them inside Rust, or?
Yeah, so some Rust code will actually call into C code. And C is like, I do think that there is like a lot of like opinions saying like, hey, this is like a really unsafe language. However, people have been writing C for a really long time. So you have a lot of like, time-tested software. And so a lot of these Rust libraries want to take advantage of this existing body of work. So then that's why they're just wrapping C. So that is also a common pattern. You can also call and do something similar from Go. You can call into C from Go and whatnot. You can probably, yeah, you can call in. You can probably call into these languages through like form function interfaces. It kind of gets a little bit complicated, but it's possible. Any other questions before I move on? Okay, so since this is kind of like this, we're talking about zero knowledge proofs, so let's talk about RISC-V as a circuit. But before that, let's kind of like talk about the concept of like ZK circuits for a second. So typically we have like a circuit as it's like program, like I kind of like see this as an arithmetic program plus inputs. And then when you run the inputs on the program, you get a receipt. And what I'm saying is I use the word receipt and proof kind of like interchangeably. But the receipt can be verified by a third party. So the interesting takeaway here is that the ZK circuits, typically the circuit is specialized for like one program, right? And the verification is typically like a constant time. So no matter how long the execution or how large the computation, verification, you will take approximately like the same amount of time. Okay, so let's talk about ZKVM circuits now. ZKVM circuits are similar, but the program itself is it's a program that can run other programs. So if you, in this way, like what we can do is generate this a proof, but we're not limited to a single program. It's more general purpose, and you still get the verification in constant time. So kind of going back to our like mental model here, what we want to do in order to generate a proof or receipt is we need the following. We need what's called a trace execution, or the execution trace of the RISC-V code, as well as a set of constraints. Okay, and so what would happen is that in a typical like virtual machine or an emulator environment, we get the program result, but in ZKVMs, you get like the result, but plus the trace and the constraints. So like what this is typically called in the vernacular is like witness generation. And then from this point on, we use mathematical operations to then generate the receipt. So then this is called the proof generation. For my kind of like mental model, I usually just think of this as the prover. Some projects like CIRCOM will split it up into witness generation and then proof generation. But to me, it's kind of like all in one. Okay, and so now, what are these constraints? Well, we talked about how RISC-V executes, right? So, about how each of the instructions have very specific rules as to what it means to be done correctly. And one example is this statement right here. Every bit should be a 0 or a 1, which can be encoded in expressions like this. So imagine like you insert a 0 into here, and then then kind of doing the math, like it reduces to 0. Or if you have 1, then this expression will collapse, evaluate to 0 as well. So I guess it should have been a double equals sign. But yeah, another constraint would be like each register should contain 32 bits of data. So basically like the process of, you have to go through the specification and then encode all of these into these mathematical expressions. Another one is like the program counter should change after each instruction. So, it'll just kind of like say, okay, after I'm done with the instruction, then I need to increment the program counter. And then, so all of the fetch, decode, execute cycles, all of those become encoded in polynomials as these constraints. So yeah, so that's a general overview, like a high-level overview of what's going on as far as like these Stark-based ZKVMs go. Any questions at this point? Yeah.
One question about constraints. Can you encode any type of logic to constraint? Like imagine you have some complex, constraint that you want to apply.
Yeah, I think as long as it can be expressed as a polynomial, and I feel like I'm not like mathematically like versed enough, but like I think there is some sort of probably like complexity. But as you make the constraints more complicated, the polynomial gets bigger and bigger, and then it just takes more processing computing to generate the proofs.
So I guess it's better to split constraints into small parts, right?
Yeah, and so what's really interesting, and I guess I can like kind of go over like what the implications are. So like the reason we like RISC-V is because it has a really small instruction set, right? So each instruction, not only is it like the instructions like a shorter list than a lot of other ISAs, but each instruction does simple things, right? And it's also modular. So RISC-V has these things called features, and then so there's a base set of instructions, which you saw in that like long column, and then beyond that, you can kind of like flip these switches on and off, like multiplication or atomic instructions, or there's some other like floating point or double precision instructions. There's also, there's actually a feature called ZK, but it doesn't have anything to do with zero knowledge. It's kind of funny. It's a hash function accelerators. And there's like fairly like specialized instructions, but yeah, so it allows us to choose. In some other instruction sets, you could be agreeing into things that may not make sense for a ZK context. One of them in particular, at least for us, is atomic instructions. Atomic instructions exist on processors to help do multi-threaded computing. And in RISC Zero's RISC-V interpreter, we only have one thread, and we don't have any notion of interrupts. So it's going to be sequentially consistent anyway. So these atomic instructions are kind of like, well, we can support them, but they don't really bias anything. So what's really nice is that we can leave those out and have that optionality. And last of all, there are existing language infrastructure for RISC-V that allows us to not like reinvent the wheel with all of these tools. I think these specialized languages, they have their time and place, but you need to build on top of that as like developer tooling. Not only that, but like also design patterns, and those take a really long time to figure out, especially the design patterns aspect, unless you're borrowing specifically from like an existing paradigm or something like that. So anyway, so those were some of the reasons. Yeah.
Can you explain like the minimal like component of it? Like
Yeah.
like how do you define minimal?
Minimal as in like, so comparing like a good comparison is like between RISC-V and WebAssembly. WebAssembly will like say, okay, the minimal supported, or like in order to say an interpreter, a WebAssembly interpreter is conformant to WebAssembly, it must implement like a lot more instructions than say RISC-V. I'm not exactly sure how many, but I think it was in the range of like 100 or so. Also, the specification kind of like moves at a different pace. With RISC-V, there is like a precedent of like, let's just be super modular and not force like some other like company or entity's needs on everyone. So it's just kind of like very compartmentalized. Yeah.
Out of curiosity, when we compare RISC-V to others, what are the limitations that already in RISC-V compared to others?
Okay, yeah, so like, I feel like this is also kind of like a philosophical debate. So like, what are the limitations of RISC-V? You get a lot of instructions. Like the code is larger as opposed to, for example, x86, the thing that this laptop runs, is called a complex instruction set. So it'll attempt to do more in a single cycle. And so kind of like the debate right now is like, hey, is our complex instruction sets like more efficient, or are reduced instruction sets more efficient? And that's kind of like this ongoing sort of battle in some ways. And so right now, it's like we see a lot of, if you think of a server, it's x86, but there are actually like new servers that are coming that have reduced instruction set. So yeah, it's kind of like, I guess one takeaway is like, yeah, the code size is larger. But like if you were to implement like an x86 or like RISC as like a ZK circuit, then the constraints could be much larger. So it's kind of like the trade-off there. Yeah.
Should have probably asked like a few slides back. It's okay, it's okay.
Oh.
You mentioned that the proofs, the receipts are always verifiable in 019.
Yeah.
But wouldn't like the proof size keep increasing if the instruction set keeps increasing?
Oh, so like what happens, and we can also talk about this a little bit later. So like the trace execution, like all of these receipts can also be compressed into a single receipt by using recursion. So
it's kind of like Mina protocol then.
yeah, I believe so. Yeah, like Mina protocol uses recursion, and we definitely use that too. Yeah.
Nice.
So. Any questions? Okay, so let's.
So many questions.
No problem.
I'm just curious, would it be like more efficient to essentially to deploy like multiple instances, right? Like compile something, right, and then interact with like multiple compiles, let's say.
Multiple what?
Like like imagine there's like a circuit, right?
Yeah.
Could you like deploy another circuit, and and the interaction with these two circuits would be more efficient?
Okay, yeah. So
is that possible?
right. Yeah. So great question. So yeah, what happens typically, like let's for example take SHA-256. SHA-256 takes like millions of rows to implement, but then like what we could also do is to encode these e-calls, like that e-call special instruction, like we can also encode these to say, okay, here's a common cryptographic operation because we're kind of like working in cryptography. So typically like these, or like large integer multiplications, the e-call kind of like allows us to extend the instruction set in such a way that it's like customized. So yeah, like we actually have like an accelerator for SHA-256. So instead of like taking millions of cycles, it can take like 72 cycles. So yeah, then that is also part of like the encoding of like, we encode that as polynomials too. So great question. So anyway, oh, okay, well, here's a slide. Cool. But wait, there's one more thing that I wanted to, so like, does anyone have any more questions? Yeah.
I have one question. So you said in the beginning that RISC Zero isn't really focusing on hardware, but there's like companies. I mean, there's a lot of talk about hardware acceleration,
Right.
zero knowledge proofs, and so on. There's also like this company, I think it's called Torrent, who's also using RISC-V for AI chips. Could you theoretically also take this what you've built and tape out a chip, and then you also basically take what you've built and then just put it into hardware and then
Right.
use that? Would that be possible?
See, that's what I was kind of thinking at first, right? But the bottleneck, I think typically like when you're developing hardware, like it's one, super expensive. And so you want to plan things out. And and RISC-V is pretty extensible. So like as we're starting to extend it, like, let's say like if our hardware manufacturer like decides now, like, okay, all these things we're gonna just like implement, but then what if we add another instruction set? And then they'll have to kind of go back to the drawing board. But the entire kind of like thing about this is that the running the program itself is not the bottleneck, but it's the proof generation algorithm. That's the most computationally intensive parts. So when we're thinking about like hardware acceleration for ZK, it's like those companies are looking at the proof generation algorithms and seeing where the bottleneck is. So like, I'm not exactly sure if it will get to the point where it will encompass like a RISC-V processor. But like for now, it's more just like doing these like optimizations for common mathematical operations used in the proof generation. So yeah. Any other questions? Cool. So yeah, then one more thing, which is kind of really cool. So earlier this morning, well, this we're based in Seattle, so it's like during the day for them. But like we have released ZKVM 1.0. Here's like a snippet from the Crazy.io. So yeah, what that means. So what this means is that we're using like the Rust semantic versionings. Like what we're trying to say is that our APIs are going to be stable. We may add things, but we're going to try our hardest to not break things by using all these Rust-based tools. And yeah, and with that combined with our verifier being on mainnet as we after we finish the TSC, it's really right now is a great time to start building. So I definitely encourage everyone here who hasn't tried it out to definitely give RISC Zero a try. So and also we also have a bug bounty. So if here's the QR code to register. So yeah, feel free to like just look at the code and see if you can find any exploits. I would say that someone has already been submitting. They have used an LLM to kind of generate these bug reports. I'm not saying that like don't do that, but like if you end up doing that, please look at the contents of what you're getting back, because it could be hallucinating and pointing to functions that do not exist. you know, I think it's like cool that we can use AI tools or like semantic, you know, static analyzers. But at the end of the day, you know, we're communicating with humans. So let's kind of like use you know, technology in a way that, you know, so that you can communicate effectively to other people. Right. Anyway, that's it from me. Thank you so much.